Hi, in a recent video I casually mentioned that one of these switchable ×1 ×10 oscilloscope probes has a drastically reduced bandwidth in ×1 mode compared to ×10. We're talking like order of magnitude or more lower bandwidth. So like a 100 megahertz bandwidth probe or a 200 megahertz bandwidth probe does not have that same bandwidth on ×1. It is much, much lower. And a lot of people were surprised by that, and I actually didn't find that rather surprising because it's not a well-known thing and it's not something that's mentioned in a lot of places at all. People just go blindly around thinking that my 100 megahertz probe is 100 megahertz regardless, but it's not. So few people ask me, could I explain why that ×1 bandwidth is lower than ×10? As it turns out, it's rather interesting. So let's discuss that. I don't think this has actually been discussed anywhere, not as a topic on its own. Anyway, there's lots of tutorials out there on how ×10 probes work and compensation and all that sort of stuff. But why is the bandwidth of a ×1 probe lower? I don't think that info is readily available out there. So let's investigate. Now, I'll just say that this certainly is not going to be a tutorial on how to use probes and why and all that sort of stuff. That needs to be an entirely separate video, and there's other ones out there. So we're just going to focus on why the ×1 is slower than the ×10 or has lower bandwidth. So as an example, we're going to look at this RP 3300 passive oscilloscope probe, fairly typical. It's a high bandwidth one, 350 megahertz, comes with the Rygold DS2000 series scopes. And this is what I showed last time in the video that caused people to ask about this. Now, it's a very typical ×1 ×10 probe. There's no compensation up the top here. The compensation is done down the bottom, but it can be done in either place. But on the higher bandwidth ones, typically done down the bottom. Now, let's take a look at the specs, shall we? Look at this. Bandwidth ×1, DC to 8 megahertz. 8 megahertz, are you kidding me? It's useless. God. Anyway, ×10, look, DC to 350 megahertz. So they sell these as 350 megahertz rated probes, but you switch it to ×1, you've got this crap 8 megahertz probe. You bought this wonderful 200 megahertz bandwidth scope and you switch it to ×1 and it's just garbage. Why? Well, we're going to find out. And because of that, of course, the rise time, big difference, 900 picoseconds, 900 puff. Look at that for ×10 and 40 nanoseconds for ×1. Huge difference, but that's not surprising considering the relative bandwidth difference there. And of course, the input resistance is going to be different between the two. 1 meg, everyone knows that 1 meg standard input impedance because it just goes through to it's basically just a bit of coax. When you put it on ×1 there, basically just a bit of coax, well, we'll see, goes all the way through to your scope. But in ×10 mode, of course, it's 10 meg ohms input impedance because of the extra 9 meg resistor in here, which a lot of people are familiar with. And of course, the input capacitance, that will come into play as well. ×10, it's only 16 picofarads, very small, equivalent to the tip capacitance, which we'll take a look at. ×1 is 100 picofarads, huge amount of capacitance there. So that will come into it. Now, the first thing you should say is, well, bullshit, show us. All right, we've got our signal generator here, we've got our scope, I've got it set to 1 volt peak to peak, sine wave at 1 megahertz, so we'll be able to adjust the frequency, and there it is, 1 volt peak to peak. You probably can't see that down there unless you're watching in HD, but that is 1 volt peak to peak. Not a problem, right? At 1 megahertz, it's, the probe really isn't introducing any attenuation at all. Bandwidth limit doesn't come into it because, as we saw, oh, by the way, I'm on ×1 here with the scope probe. I can switch it to ×10, of course, and there we go, we get 1/10 the amplitude. So we're on ×1. So let's actually adjust the frequency here up and see if we do get that rated 8 megahertz bandwidth. So, because we're 1 volt peak to peak, it's specified typically at -3 dB bandwidth, which should be 0.707. So, if it's 1 volt peak to peak, it should be 0.707 volts. Let's say 0.7 volts peak to peak. So here we go. We'll wind the frequency up. 2 megahertz, 3. Aha, you can see the amplitude dropping. Look at that. Let's see what we get at 8 megahertz. There we go. We're getting 800 millivolts. So it's actually, bandwidth is better than what it says on the data sheet. And 707. Let's go down. Probably can't read there. There we go. That's practically 0.707, 10.1 megahertz bandwidth of this probe on ×1 mode. Oh, useless. And of course, if we keep increasing the frequency on that, I'll go up a digit. Here we go. And we're up at 40 megahertz, 50, 60. See, this is a 350 megahertz rated probe. And it's there's 150 megahertz. Useless. I mean, you know, yeah, we're still getting something down there, but, you know, I mean, the attenuation is absolutely horrible. And we'll switch it to ×10. Here we go, and we'll do the same thing. We've got to turn our vertical up there, and we're at 1 megahertz at the moment, and let's keep going. There we go. It's dropping a little bit, but I think that's probably... Oh, no, it's going back up a bit. So that's probably the amplitude stability of this Rigol function gen. But we're up at 160 megahertz now. And that, well, 160 megahertz is the maximum frequency of this SIG gen. But there you go. It basically did not drop in amplitude. You know, there's a little bit of change there, but the amplitude stability of this, I don't know the spec. But basically, that probe is just fine. It is not attenuating at all because it has a rated bandwidth of 350 megahertz on ×10 mode. And of course that bandwidth limit is going to kill any high frequency content, like this square wave, for example. Here's a 10 megahertz square wave on ×10 mode, so a bandwidth of our probe is 350 megahertz, and of course it looks like a square wave, and we can see the overshoot and the actual signal fidelity in there. But if we switch it to ×1, look at that. Wah, 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 wah. Bandwidth limit of that ×1 probe. It's useless. Now, you're probably asking yourself at this point, something smells a bit funny here, because isn't like scope probes supposed to be like good quality coax? And when you put it on ×1 mode, it's just a bit of coax going in, right? Well, yeah, it should be. So let's get a bit of coax. There we go. And let's whack it in there and see what we get. Here we go. Look at that. A bit of overshoot there. Bit of ringing because it's not terminated properly. But let's increase this in frequency. We're at 1 megahertz there. So let's wind it up. And as you can see, 40 megahertz, 50 megahertz, no problem. Look at, well, it's rounding off there, but let's not look. But there is no attenuation of that signal by just a bit of coax. So why is your humble oscilloscope probe got a lousy 10 megahertz, barely 10 megahertz bandwidth on ×1 mode when it's supposed to be just switched directly through? Let's go to the whiteboard. And ta-da! Here we have the circuit of a typical ×1, ×10 switchable probe. You may have seen these before. Yes, this is a new whiteboard mounted on the wall. Isn't it neat? And yeah, you may have seen this circuit all over the place. Very typical. There's lots of articles and tutorials on how ×10 compensated probes work. We won't necessarily go into that here. What we want to find out is why that pesky ×1 probe has that really low bandwidth. So let's start out at the tip over here. Here's the probe tip. There's a little bit of probe tip capacitance. They don't often show this in the circuit. They just show the typical 9 meg resistor and the compensation cap. But we'll show it because it's actually rather valid, and it'll come from the data sheet as well. These are all going to be typical values, of course. They will kind of vary, but let's just go for typical. Now, on a ×10 probe, you have a series 9 meg resistor in here. So it voltage divider with the 1 meg input on the oscilloscope over here. It forms at DC, forms that ×10 divider. They call it ×10. Yeah, I know, it's really weird. It's divide by 10. Now, of course, there has to be a compensation cap across that 9 meg resistor to take into account the AC bandwidth of the probe. So you've got to compensate that for your input, because the input of the oscilloscope here also has about 15 picofarads of input capacitance. Very typical across the 3 scopes I've got here, even from the 500 megahertz Agilent right down to the DS1052E. They're all around 15 picofarads, plus minus a few picofarads input capacitance. So that is designed to compensate for that. Ignoring the coax at the moment, just assume it's an ideal coax ideal transmission line, and that's all there is to it. Now, there is actually 2 different schemes, and I've shown you before. There are these types which have the compensation not in the probe tip here, so this capacitor is actually fixed. It's not variable like I've shown here. The variable capacitor is over here in a little RC network. Over here, typically going to be a series resistor in here with an adjustable cap, 0 to 50 picofarads, something like that. Exact values are going to change depending on how the probe is actually manufactured. And typically your high bandwidth ones are, you won't get the adjustment in the top here. You'll typically get it at the base down here. But you can also get the lower bandwidth ones which have the adjustment in the top here. So they actually have the adjustable capacitor in there, the trimmer cap, and they don't have any network down here, so the coax just goes directly into the scope. So you can ignore that, those components don't exist. All you got is the 1 meg and 15 picofarad input capacitance of your scope. Now let's take a look at a ×1 probe and how that works here. And you've noticed I've added some sneaky little calculations in here. Now, how a ×1 probe works? Incredibly simple. All it does is it's got a switch in there and shorts out the 9 meg resistor and the compensation capacitor. That's it. So these no longer exist. So you've got a direct connection from the tip directly through to your oscilloscope input. And of course, if you don't have that network there, you've got nothing. So all you've got is your tip capacitance. You've got the capacitance of your coax, which let's just say it's 100 picofarads for a meter. For argument's sake, it's going to vary depending on the type, but let's just say it's 100 picofarads, and once again that will be, you know, equivalent to another capacitor in there like that, distributed, whatever, capacitance of the coax and the capacitance of your scope input and your 1 meg input resistor. So you would think that, okay, you've got all this capacitance on here and it's going to have an impedance at frequency. Now you should know your formula for capacitive reactance, or the effective AC resistance of the capacitance at a frequency. It's 1 over 2 pi FC. So let's take an example of 10 megahertz, which is roughly the bandwidth of the ×1 probe we measured, and let's plug in these values of 15 picofarads, which we got here and here, and that works out to about 1K. So at 10 megahertz, you've effectively no longer got a 1 meg ohm oscilloscope input here. You've got 1 meg in parallel with 1K here, in parallel with 1K here, and then the capacitance of the coax, 100 picofarads, that's about 159 ohms at 10 megahertz, so very low. Your 1 meg input impedance scope is now like, you know, 100 ohms or thereabouts. Incredibly low input, but still, let's say you've got no load-in effects on your circuit, you're driving it with a low impedance load, then your signal should go faithfully directly from the input through to the scope without any attenuation. So why are we getting the attenuation on that drastic attenuation, about 10 megahertz bandwidth on the ×1 probe, whereas a bit of coax, which is essentially exactly the same thing, it's just, well, let's say it's longer, you know, it's got 115, then effectively, what's the difference between the ×1 probe and a bit of coax? There shouldn't be any difference, but there is. We measured it. Why? Think we can solve this one with a multimeter. Now before we get to the multimeter, let's just have a look at the input specs again and see how they relate to what we've seen on the whiteboard. Let's look at the input capacitance here in ×1 mode, 100 picofarads. Now that's effectively the capacitance of your coax cable only, because the ×1 switch of course shorts out the input compensation network and all you're left is with the coax. But it can actually also include the compensation network if you've got it at the end of the cable like here. At the scope end, rather than this one here, which it just has the coax going directly into the scope. And that is, like in that case, they'll have the compensation network up here. Now there's actually not much difference between having the compensation network in here and down at the end of the probe down here, you can the performance can be the same effectively. Depends on how you tweak it and actually design it. But most of your high performance times 10 probes will have your compensation network down this end here. Now, if we have a look at the times 10 mode here, it's 16 picofarads, an order of magnitude less effectively. The reason for that is the effective tip capacitance. And I say the word effective because it not only includes the small amount of capacitance between your tip here and your input compensation network in here, you start your 9 meg resistor down in there, but it's also the effective reflected capacitance from your coax as well. So it's that 100 picofarads, but because we've got a times 10 divider in there, that capacitance gets divided down and then becomes effectively 10 times less at your tip. So that's why that one's 10 times less. This one's a little bit high at 16 picofarads, usually a little bit less than that. Usually you'll see an order of magnitude difference between those. And also this is why your fixed times 10 probes can have a better performance than these compromised times 1 times 10 probes, because your compensation network can be right at the tip. That 9 meg resistor can be right up there and there's bugger all tip capacitance, whereas this one's got just a little bit extra and a bit of extra transmission line in there as well to deal with. So yeah, your fixed times 10 probes are always going to be higher performance, or can potentially be higher performance than these switchable compromised probes. And that's why a times 10 probe is highly valued, because it has a much lower input capacitance than your times 1. So it loads your circuit down much less at high frequencies. That capacitive reactance formula we looked at, remember that? Now, what we're going to do, we've got our regular coax here. It's just like 1/2 meter of coax, and we're going to measure the center conductor. And, well, no surprises what we're going to get here, folks. 0 ohms. There you go. It's a direct short because the coax just goes directly through. Yeah, it works as a transmission line and everything else, which we won't go into today. But what happens if we measure this scope probe on times 1, by the way? So let's put it on times 10 first, okay? And we should get our 9 meg that we looked at on the board there. There it is, spot on 9 meg, no worries. But we switch it to times 1 and there should be nothing else in there but the switch, right? That's it. You'd expect to get exactly the same as the coax, do we? There we go, 330 odd ohms between the tip and down here. What is doing that? Is there a series resistor in there? Well, to show you that there's nothing, no funny business going on in this tip here, I've taken apart a times 10, switchable times 1 times 10 probe. Yes, it is different to the Rigol. It's not a Rigol brand, it's a Velleman brand. It's just a cheap ass old one I had lying around. And there's the times 1 times 10 switch. So times 10 is down in that position down there. So we're up in times 1 position, and that should short out the network there. So the compensation network. So let's measure between that probe point and here. What do we get? A dead short. So there's no funny business going on inside that probe, what we'll call the probe. It must be in the coax or the end of the coax. And here's the part of that chopped off Velleman probe, and let's measure it. There we go, and the fine wire, I'll get a very good close-up of this in a minute, but basically I'll have to hold my finger on there, I'm not touching the other one. There you go, 230 odd ohms. This oscilloscope coax, and trust me folks, there's no series resistor or other circuitry inside there. I could chop it open to prove it, but I don't know, couldn't be bothered. Oscilloscope probes do not use regular coax like a regular coax cable. These are what's called a lossy transmission line. They're designed to have that high resistance. And check it out, that's what's inside an oscilloscope coax cable. It's a single strand there. No, I haven't actually, when I stripped it, no, I didn't accidentally cut off all the other strands. It is a single tiny strand like that, and often it is, you might be able to see that it's actually not entirely straight. It's actually got little kinks and bends in there, and that's actually designed in some of the more higher quality ones. Remember, this is only a 60 megahertz Velleman heap of crap. And that's what these probes are optimized for. They're optimized for their times 10 mode, the high bandwidth mode, which is why they are going to use this lossy transmission line, which has typically, most probes are going to have a couple hundred ohms. It will vary by plus minus a couple of hundred. You know, the actual DC resistance isn't in actually, you know, it's important, but it's not the main, you know, driving factor. Transmission line design theory, I won't go into it. It is actually quite complex. I may have to do a separate video on this, actually simulating all this stuff and exactly how it works. But these probes are optimized for, or the transmission line, coax, the lossy transmission line, is optimized for the high bandwidth times 10 mode. So the times 1 mode is actually just a bit of a kludge added on, and that's why we're crippled with the low bandwidth on the times 1 mode, because they're trying to incorporate both features into a times 10 probe. So I stripped a bit more of that out, and you can see somewhere along here the crinkled nature of that wire. There it is. See, it's sort of crinkled, and some of your more high performance ones are much more crinkled than that, and presumably they do that to help with the flexibility of the cable. And of course, but you'd have to take all that into account about the final resistance, because this is actually not just regular wire, of course, it is resistance wire, which has a certain specific high resistance designed to match the compensation networks, and that's how the whole probe is able to get its high performance. I mean, this is only a 60 megahertz one, so this isn't a particularly high performance one at all, but you can see the white foam insulation in the core there, and that'd have a very low dielectric loss, very specifically chosen for the task. Then there's a black outer protective jacket there, and then the braid shield, and then the outer jacket on top of that. So there's a lot of art and science which goes into the design of these probes, and then the matching, or the coax used in these, and then the matching compensation networks to give you a flat usable response up to, you know, in some cases well over 500 megahertz, which is really amazing technology. So these aren't just regular coaxes. So after that little investigation, what are we left with? We're left with the knowledge that this bit of coax ain't a bit of coax. It's a lossy transmission line. It has DC resistance in there, and that's going to, which we measured at around about 330 ohms. So that now, we have an attenuator. Whenever you've got a series resistance and a resistance at the other end, you've got an attenuator. So let's look at the entire circuit we've got now for our times 1 probe. Okay, these don't exist anymore. Our resistor and cap don't exist, so that just goes straight through, wired straight through like that. This 1K really doesn't come into the equation at all, so it may as well not even exist. So we'll leave that out, and we've got 330 ohms now in series with, let's take out our compensation network here. Let's assume we have a probe that doesn't have the compensation network at this end, and then our 15 picofarad scope input has now become a 1K resistor as well. So we effectively have 330 ohms in series with 1K. Ignore the 1 meg, it's a couple of orders magnitude bigger than the 1K, so it doesn't matter. A rough rule of thumb, if something's an order of magnitude bigger, 10 times bigger, you don't worry about it, you just take it out of the equation for back of the envelope type calculations. So if you do the math with that 330 ohm and the 1K over here, which is the impedance at the roll-off minus 3 dB roll-off frequency of 10 megahertz we measured, it's around about that minus 3 dB point, or that 0.707, I think it's 0.75, or something like that, near enough. So that's what determines your upper frequency limit. This series resistance and your capacitive reactance of the input is scope. But of course it gets a little bit more complicated than that, because that 330 ohms, yes, it's at DC, and yes, it's going to be quite similar at AC as well, but this is because it's a distributed resistance, it's actually all the way through here. So I've shown this is all different resistors in there, and this is how you can actually simulate the thing using the lumped model like this. And then you've got the individual capacitance is in here, and there will also be inductance as well in any model of a lossy transmission line like this, but I haven't shown any of the inductors. So of course that's 330 ohms at, let's just say it's going to be constant at AC and DC. The input is going to be different at DC. At DC, we're going to have our 1 meg. So that's why down at the low frequencies with the ×10 probe, this 330, the resistance of this coax doesn't matter at all, because 1 meg. Do your voltage divider math there, and this doesn't matter a rat's ass. So the higher frequency you go, the greater attenuation you got, and you can muck around with all little R's and C's and stuff in the lumped model, but basically you're going to have that upper frequency. So you're going to get that frequency roll off that looks like that at a certain frequency, and it's going to be 3 dB down at about 10 megahertz there. If that's your 1 volt input, it's going to be 0.707 as we measured on the scope. It's going to have a roll off because you've got effectively a capacitor here which changes with frequency, and let's say a fixed series resistor element. So why do they even bother having these switchable ×1 ×10 probes if the ×1 mode bandwidth is useless? Well, it's just convenience. Essentially they design these things for the high bandwidth on the ×10 mode, but that by nature of its very design with the lossy transmission line, it just cripples the ×1 mode and makes it pretty much useless. Well, it's not useless, it's just low bandwidth. So the rule is, if you want high bandwidth and you don't want to attenuate your signal, which the ×10 probe does, that's one of its disadvantages. One of the advantages of the ×1 mode is you're not attenuating your signal by 10 times, then use a regular coax. And of course you can get very high bandwidth probing with just a regular coax if there's various termination resistors on the input and stuff like that. These can be very high bandwidth probes. Incredibly low impedance, of course, because you've got the direct capacitance of the coax there and at high frequencies, but if you want high speed with no attenuation, then just a regular coax can be useful. And I might do a video on that too, and there's other videos out there that explain that. So why do they go to all the effort to have a lossy transmission line in here when you can just use an ordinary coax? Well, this is the technique that they use to ensure the widest bandwidth possible in a ×10 probe, and also the flattest bandwidth possible over that mode. So it doesn't, at the end of the bandwidth, doesn't ring up like that or doesn't go down like that or anything like that. It does no funny business. It's a lot of art and science goes into this, and it was originally developed by Tektronix way back, and they were the ones who pioneered the lossy transmission line technique. And they're very cleverly and very carefully designed to get like the your 500, 600, 700 megahertz bandwidth passive probes, which you take for granted these days, but you're paying a lot for that. And there's a huge difference between a cheap ass 60 megahertz probe and a 600 megahertz passive probe, and that's often why they cost so much. They're very difficult to actually get right and trim and get it all right in terms of the compensation network in here that we looked at, matched to the actual physical properties of the coax. So a lot of art and science goes into just designing the physical properties of that cable, getting that little wiggle inside exactly right, getting the lossy parameters all right so that they match, and you don't get any funny business, overshoot, undershoot at the end of your bandwidth and all that sort of stuff. That requires a whole separate video though. Whew. Well, that was a lot of talk just to get to the simple conclusion that a oscilloscope probe coax actually has a lossy transmission line resistance in it. I could have just told you that at the start and saved you, 15-20 minutes worth or something, but I hope you found that interesting, and that is why these ×1 probes have a lower bandwidth than a ×10 probe, order of magnitude or greater. It's something a lot of people don't know. So I hope that was useful, and if you want to discuss it, jump on over to the EEVblog forum, and if you like the video, please give it a big thumbs up. Catch you next time.